In this video, we'll talk about the error bound that we get from the alternating series test and how it can be used in computing alternating series. So, one thing to realize from the alternating series test, like some of our other tests, is it doesn't give us a way to actually find the value of the series. It just tells us that it converges and nothing more than that. Because there's no way to actually say, here's the value as well. But because we have a nice control over how the alternating series behaves, we can get a pretty good estimate on what the result should be from a partial sum. So let's take an alternating series where Bn is positive decreasing going to 0. Then what do I know? Well, I know that if I take the partial sum up to n terms and compare that to the actual limit, the actual series, my error is no more than the first term I leave off. So what this basically says is, since I know that my bn's are going to 0, I can eventually make the error as small to whatever I want, and I can then approximate my full limit by this partial sum to within this error. So like we had for errors for integration, this is another error calculation. The point is the error is no bigger than the first term I leave off of my series. This means we can do a really good job approximating with partial sums, provided we know how many terms we need in the partial sum to get really close to the actual limiting value. So why is this true? What's the whole zigzag argument from before, right? If I'm here with my partial sum Sn, and then Bn plus 1 takes me up here to Sn plus 1, I know that my limit for the series must be between these two lines, which means I can't be off by any more than Bn plus 1 if I take Sn to be my approximation. That's the basic idea, and it works either way with the up and down for the zigzags. How can we use this? Analyze this again, conditionally convergent series that we had before. Does it converge? And what do we know about it? How close is S10 to the limit? Well, so we know it converges conditionally. That example was in a previous video, right? The point being our Bn here is 1 over n, which is decreasing, positive, and going to 0. But the sum n equals 1 to infinity of 1 over n, which is the absolute value series, is divergent. What else do we know? We know the limits between 0 and 1 because 1 is the first term. How close is S10 to the limit? Well, it's off by no more than the first term I leave off by taking S10. Right, so S10 is the sum from n equals 1 up to 10 of negative 1 to the n minus 1 over n. So the first term I leave off is the n equals 11 term, and that's B11, which is 1 over 11. What the error bound tells me is that the difference between S10 and S is no more than 1 over 11. And that's what I get for the error bound. You could answer another question like this if it said, how many terms do I need to be within 1,000th or 0.001 of the limit? And the answer there is then 1,000 terms, because then my next term, 1 over 1,001, is less than the error bound that I want. So to wrap up this, let's look at two examples where we want to talk about convergence or divergence of the following series. Both of these we see are alternating series. So in order to see if they converge, we must first look at, do they satisfy the conditions of the alternating series test? So this first series here we have is sum n equals 1 to infinity, negative 1 to the n times n over root n squared plus 1. If this was going to work for alternating series test, I would see that Bn must be n over root n squared plus 1. Now the problem I'm seeing with this one here is what happens as n goes to infinity? Well, in this case, the limit as n goes to infinity of Bn is 1, because I effectively have a power 1 on top and a power 1 on the bottom because it's an n squared inside of a square root, which is not 0. So the alternating series test does not apply. However, that isn't enough to tell me if this converges or diverges. It just means I can't use the alternating series test to work it out. The issue here is the fact this limit is actually 1, implies that the limit as n goes to infinity of the actual terms of my series, negative 1 to the n over n squared plus 1, does not exist. Because I have things going to 1, but they're being alternated by a plus or minus sign. So they're going to both 1 and minus 1 kind of at the same time. So this limit does not exist, which means this limit does not equal 0. And so this series diverges by the nth term divergence test. For the second example, sum n from 1 to infinity, -1 to the n over n ln of n. This one we're more lucky. For Bn being the sequence 1 over n ln n, we get exactly what we want. This is positive, it's decreasing, and it goes to 0. Because both n and ln are going to infinity, as this goes to infinity, this whole thing goes to 0. Therefore, this converges by the alternating series test. So there's the idea of what the error bound is for alternating series test, and then how you can use this to talk about convergence or divergence of series. It's important to also realize that because this test doesn't apply, does not mean that something automatically diverges. You must have another argument to get you to the fact that it diverges in order to actually conclude that for a series. This gives you an idea of how this all works and how you can use this to evaluate whether certain series converge, given that they are alternating series. As well, what you can do to estimate the actual sum of those series using partial sums by the error bound lets you say how close you really are to the actual limit when you take a partial sum of this series.